All right, good afternoon, everybody. I wanted to talk to you about experiment number 7. Now, experiment number 7 has a couple of different parts to it. This is an experiment all about precipitation and reactivity of metals in a solution. So for part 1 of the procedure, there are basically no changes to be made. For parts 2 and part 3, however, it's very important that you attend to these changes that are going to be made. Now, in a nutshell, part 1 asks the question, well, if a metal reacts with a solution, and this reaction is really on the basis of something known as oxidation and reduction. So if you look on page number 113 of your lab manual, you'll see something known as a metal reactivity series, or an activity series of metals, which shows a metal, for instance, at the top, lithium, Lis, yields Li plus Aq plus an electron. This is an example of solid lithium, which is depicted right here, well, transforming to form Li plus, which is a lithium cation, and a single electron. Now, if you think about this in terms of charges, a positive charge and a negative charge, those would combine to make 0. So effectively what we have is solid lithium with no charge whatsoever in its elemental state, reacting to form a lithium cation and an electron. Now, what's happening here is that solid lithium right here is losing that electron. This electron goes wherever, but we're left with this lithium cation. Now, this is an example of oxidation. Solid lithium, and we're looking at this from the perspective of, we're reading this reaction from the left to the right. So lithium transforms into a lithium cation and a free electron that's gone off. So this is an example of oxidation. Now, if you rewrite this, and again, you're reading from the left to the right, if you rewrite this as Li plus Aq plus E, so that would be a lithium cation adding an electron, and you form Lis with no charge whatsoever, that would be an example of reduction. So to put it simply, oxidation is when something loses an electron, whereas reduction is when something gains an electron. So one way that you could say this top reaction is solid lithium gets oxidized. One way that you could sum up this reaction on the bottom is you could say that this lithium ion was reduced. So that's kind of the principle upon which we're looking at our reactions. Now for part 1, what you're going to be doing is you're going to be using a total of 3 different solutions. One is zinc chloride. Another, and this is a semi-soluble solution, we're going to characterize it as aqueous though. We are also looking at NiSO4. That is also an aqueous solution. Now this zinc chloride is a little bit cloudy, a whitish, so it's not completely soluble, whereas nickel sulfate is very soluble. Then the last solution is copper chloride, which is also highly soluble. What we're going to do is we're going to add a metal, unknown number 1/A, unknown 2/B, unknown 3/C. We're going to add it to each one of these, and we're going to add it to H2O, which will serve as our negative control. Now, when we add these metals to these different solutions, what we're doing is we're simply looking for, is a reaction taking place? And what we're going to use that for is we're going to use that to identify what our metal could possibly be. Okay, So one way that you can kind of understand that is if you again look on page 113 of your lab manual, you'll see this activity series. And what this tells you is to look at a chemical reaction or sorry, it tells you to look at a metal and an ion. So one way that you could sum this up is if a metal is above the ions in the activity series, then that metal will be oxidized. Okay, so examples that are presented. If you mix zinc metal, Zn, zinc is near the top, or actually it's kind of mid-range on the activity series table. If you mix zinc ion or zinc metal, so Zn solid, plus copper ions, copper forms a 2+, a divalent cation. If you mix those together, what's going to happen is zinc is going to lose electrons and copper is going to gain electrons. So your end result will look a little bit like this. Zn2+, and that would be aqueous. So zinc is losing electrons. Zinc is being oxidized. Those two electrons, where are they going? Well, they're going to copper. And we're going to form CuS. Therefore, copper 2+, the copper cations, are being reduced. So what we're going to do is take these metals and mix them with these different solutions. And based on whether or not that metal reacts with a solution, we're going to be able to deduce, or at least narrow down, what are possible identities for our metal. So as an example, if you had solid lithium, lithium is the most easily oxidized metal on the activity series. It's at the very top. If you took solid lithium and put it in each one of these solutions where there are zinc ions or nickel or copper ions, that that lithium is going to react. Now, if something, for instance, if you had solid chromium and you mix that with zinc ions, chromium is below zinc on the activity series table. So if you had solid chromium and add it to zinc ions, no reaction is going to take place. Whereas if you took that chromium and you added it to nickel ions, chromium is above nickel. Chromium is going to transfer electrons to nickel, and therefore you're going to see oxidation of chromium, reduction of nickel. So what you're going to do is say, does this metal react with zinc, nickel, or copper? If it reacts with all of them, well, then it has to be above all of them on the activity series table. If it doesn't react with any of them, well, then that metal has to be below all of those ions. If it reacts with one but not the other two, well, then where would it be? That would mean that it's above one of them but below the other two, or vice versa. All right, well, that's part one. So you're going to work to identify what the possible identity of those metals are. Now for part two, what we're going to be doing is we're going to be using, as it's described on the procedure, you're using 8 solutions. We're only going to be using 6. The 6 solutions that we're going to use are NaOH, KOH, NiSO4, K2CO3, CuCl2, and CuSO4. So what we have there are sodium hydroxide and potassium hydroxide, nickel sulfate, potassium carbonate, copper chloride, copper sulfate. Grand total of 6 solutions. What you're going to do, if you look on page number 115 of your procedure, this tells you to develop or to put together a matrix on your 24-well plate. And in that matrix, you're going to mix your strong bases, which, spoiler alert, this is a strong base and this is a strong base, NaOH and KOH. you're going to mix that with each of the other 4 solutions. And for the sake of simplicity, I'm just going to label them A, B, C, and D. You're going to mix sodium hydroxide with both, or sorry, you're going to mix solution A, a nickel sulfate solution, with both of those strong bases. B, with both of those strong bases. C, with both of those strong bases. And D, with both of those strong bases. Now, what you're going to ask yourself after you've mixed these 2 solutions, which you really don't need much more than 1 milliliter, you're going to say, does a precipitate form? And a follow-up to that is, what is that precipitate? Okay, now what's important to recognize about all of these solutions is that they are all soluble, or they are all aqueous solutions. So essentially what we're looking at is we're looking at a molecular reaction, an ionic reaction, and a net ionic reaction. So we're looking at those different reactions. Now I'm going to do basically a rundown of what's on page 117, because what we're looking for is, does a solid form here, 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 here? And we're trying to find out what that solid is. Okay, so let's say hypothetically that nickel sulfate and sodium hydroxide are mixed together. Now, we are looking at our molecular reaction. NiSO4 plus NaOH. What's that going to yield? Well, this is a great example of a double displacement reaction. We've got AQ, AQ. Okay, so we have nickel sulfate, sodium hydroxide. We have kind of the model of AX and BY. You're going to mix those to make AY and BX. Okay, so that would give me NiOH. Now the question here is, well, is that the right ratio? Is it 1 nickel ion to 1 hydroxide? And I'll tell you that it's not. How do I know that it's not? Well, I know that it's not because sulfate is SO4 2-. I have no charge indicated here. Therefore, this nickel must be a +2 ion. So since nickel is a +2 ion, hydroxide is a -1 ion, I've got to have NiOH2. My other substance is, well, sodium and sulfate. Sodium is +1. I say plus Na. And then sulfate is -2, which I already talked about. So this is going to be Na2SO4. All right, so now what I have is I have all of my different components present, but I haven't balanced my chemical reaction. And that's where I'm going to go next. So whenever I'm balancing an ionic equation, well, what I'm going to do is I'm going to look at my ions. I've got 1 nickel ion, 1 nickel ion, 1 sulfate ion, 1 sulfate ion. How many sodiums do I have? Well, I got 1 over here and I've got 2 over here. So then I've got 2 hydroxides. If I put a 2 in front of there, I'm balanced. Okay. Now, hydroxides are quite often insoluble. And nickel hydroxide is a great example of an insoluble hydroxide. So what I need to do is I need to write my ionic equation. And my ionic equation shows each of my components broken down, if they are aqueous, in the ions in which they exist. I'm going to go ahead and write S next to my product of nickel hydroxide. Then I'm going to write AQ for sodium sulfate. Now, I've got Ni2 plus, I'm on my ionic equation, AQ, plus SO4 2 minus, AQ, plus, and now I've got 2Na plus AQ, plus 2OH minus AQ. That's going to yield NiOH2 as a solid. Now I kept this around as one intact thing because this is existing as a solid. So I'm going to pair those two things up because they precipitate out a solution. Then I'm going to do, well, my next ions is 2Na plus AQ. I move that from a subscript to a coefficient because of the fact that I have two of those sodium ions, and this is an aqueous solution. So I've got 2Na plus SO4 2 minus AQ. Okay, so there's my ionic reaction. It is balanced. Everything's straightened out there. My net ionic equation, well, my net ionic equation is the ionic equation, but simpler. So all that I really need to do for the net ionic equation is identify my product. My product was NiOH2 solid. What else is there? Well, I got to find out where those two things came from. I've got Ni2 plus aqueous and 2OH minus aqueous. Donezo. So that would be an example if that solid forms. Now, with that said, on page number, like I just said a moment ago, hydroxides generally are insoluble. I want to make a change to your procedure or to your output on page number 117. On 117, you have a molecular ionic and a net ionic equation. And then you have another block that is a molecular ionic, net ionic, and then a third one, molecular ionic and net ionic. Okay. Now, the headlines or the caption above each one of those, for the first one, it's going to remain the exact same. The second one says, in the space below, write the molecular net ionic and ionic reaction for the combination of calcium hydroxide and hydrochloric acid. You're not going to do that. Instead, you're going to write the combination of molecular ionic and net ionic for a second PPT or precipitation reaction. Then same thing for the third one, but it's for a third PPT RXN. A little bit of a spoiler alert, there's going to be at least 3 precipitation reactions that take place. So that I hope will help you out. Okay, now the last part of this procedure is going to change pretty dramatically. And that is part 3. Part 3 of the procedure asks you to collect 15 milliliters of 2 different solutions. You're not going to do that. Part 3 says, based on what you saw in part 2, well, which solution combination generates this product? What we are going to do is instead, you are going to use the information that you got from part 2 and do a calculation for a theoretical yield. If you look at my data sheet right here, there are several things that I've omitted. For instance, right here, and right here, and finally at the bottom. The things that I have omitted are the mass of the debaffled coffee filter, the mass of your watch glass, mass of your filter, watch glass, and your solid, mass of, and then your approximate incubation time in the oven, and actual mass of the solid recovered. We are not doing those things. Instead, what you are going to do is you're going to look at part 2. And you are going to say, well, which combo gave me a product, a solid? You are going to, like I said previously, there are multiple combinations that give you solids. So you're going to pick a combination. So just for consistency, I just did the net ionic equation for nickel sulfate, and sodium hydroxide. So let's go ahead and say NiSO4 plus NaOH. You're going to use the balanced chemical reaction that you just came up with. Now, one of these can be identified as a strong base. One of these can be identified as a non-strong base. Well, spoiler, sodium hydroxide is a strong base. I'll leave you to figure out which one of them is a non-strong base. What you are going to do is you're going to fill out your data sheet where it says, what's the concentration of that strong base? What's the concentration of that non-strong base solution? Then you're going to take, or you're going to imagine that you used 15 milliliters or 0.015 liters of each one of those solutions. You're going to multiply that by the concentration of those two solutions. Well, the sodium hydroxide solution that you're going to be using in lab is 0.75 molar. The nickel sulfate, I believe, is 0.25 molar. You're going to figure out the number of moles of that sodium hydroxide solution. So you're going to take 0.015 times 0.75. Then you're also going to do 0.015 liters times 0.25 molar. Okay. Whenever you do that, you'll come up with 0.015 times 0.75, 0.01125. Then you will also do 0.015 times 0.25, which will give you 0.00375. This is the number of moles of each of these components. Now, what you need to figure out is something known as the limiting reactant. Based on these two reactants, which one of them is going to limit the amount of the product that's produced? And the easiest way to figure this out is by using your balanced chemical reaction. So I'm going to rewrite my balanced chemical reaction, which is NiSO4 plus 2NaOH yields Na2SO4 plus NiOH2. Got it balanced. What I have, coefficients. The coefficient in front of nickel sulfate is 1. The coefficient in front of sodium hydroxide is 2. This right here is the number of moles of sodium hydroxide. This right here is the number of moles of nickel sulfate. In order to figure out my limiting reactant, all that I'm going to do is I'm going to take the number of moles and I'm going to divide that by by my coefficient. So 0.01125, I'll divide that by 2. 0.00375, divide that by 1. And 0.01125 divided by 2 gives me 0.005625 and 0.00375. This number is smaller, therefore it is my limiting reactant. So that, by virtue of this number being smaller, I've identified my limiting reactant. Now that I've identified my limiting reactant, I can say something about, well, that controls the amount of my product that I'm going to produce. So what I'm going to do is I'm going to go to a clean slide, and I'm going to do the dimensional analysis for my theoretical yield. I know that I have 0.00375 moles of NiSO4. And what I want to do is I want to know how much of my product, which in this case was my nickel hydroxide, how much of my product that I'm going to generate. So I have my moles of NiSO4. I've got 1 mole NiSO4 And this right here, this is coming from my balanced chemical reaction. My moles of nickel sulfate, my reactant, to nickel hydroxide, my product. 1 mole of nickel sulfate is 1 mole NiOH2. Now, to answer this question, what I'm looking for is, well, what is my molar mass of nickel hydroxide? And well, you can get that from the periodic table. So moles of, and as I proceed through my dimensional analysis, my moles of nickel sulfate will cancel. I'm left with my moles of nickel hydroxide. So I'm going to put that on the bottom, NiOH2. What is the molar mass of nickel hydroxide? Well, based on the periodic table in the back of your lab manual, you've got 58.693 grams per mole for a mole of nickel, plus oxygen. I'm going to just round it up to 16, and there's 2 of them, so I'm going to say that's 32, plus hydrogen, they're about 1 each, so plus 2, so that would be, and I don't know why I put so many parentheses in there. Let me erase those. There we go. Oh, 32 plus 2 is 34, plus 58, that would be math. Oof. Be 34 plus 58. Oh man, 34. I'm using my calculator right now because I don't want to get it wrong. Okay, 92.693 grams per mole. So 92.693 grams. Plug that in. Now remember, you multiply across the top and divide by the bottom. 0.00375 times 92.693 divided by 1 is 92.693 times 0.0375 is 0.34759875 grams of nickel hydroxide. And for the sake of organization of our numbers, we got 3 sig figs, and I'm going to use scientific notation. So I'm going to say 3.48 times 10 to the negative 1 grams of NiSO. NiOH2. All right, so that is working through parts 1, 2, and 3 of your procedure, and it's important that you do all of that. Now, for your reflection questions, omit question number 2. That's all I got. If you got any questions, ask your IA or send me an email. Have a good one, and good luck with your exams and everything like that.